Hey everybody, so I wanted to make this video to show off and showcase a real-world example of FOPC, which is first order predicate calculus. I know calculus, it sounds advanced. I won't talk about math a lot in this video, so essentially all we do is to set this up. I have a few pip installs, and I'll leave the link to this Google Colab in the description of the video. So it's just pip install transformers, and then pip install transformers, the EI and OPS package specifically, which we need for the Phi 1.5 model, and then torch, and then also the auto model for causal LM for our tokenizer. And then we're loading directly to the GPU, and then again I'm using the Phi 1.5 model, and then just loading the model in, and then testing the model here. Print essentially all primes between 1 and a number, and then it does reports back between 1 and 20, all the primes. And then here I start experimenting around, and then so how I had this set up. So if you run this by default, it's going to do the same thing. So this was my control at first, and then I have with no so you can just use this and then run it and then get with no prior context, right? So the model, if you run this the first time, it'll have no context with it, and then so you can use it as a control to test whatever you want. And that's what I was doing with this model. And then I have down here, you want to run this context, this one first, this one, and then you want to run the prompt. So just run the context and the prompt, and the context is literally just the context. And then the context is what first order predicate calculus is. And then so it's just logical reasoning using first order predicate calculus is a powerful way to express knowledge about the world and to draw conclusions from that knowledge. First order predicate calculus uses variables, predicates, and quantifiers to represent objects, their properties, and the relationships between them. For example, the sentence "it is faster to fly than to run" can be expressed in first order predicate calculus as, and then the equation that essentially all fly faster is run. So it's always faster to fly than to run. It's essentially, if we're reading out that equation, that's what it says. And then this sentence means that for all objects x, if x is flying, then x is running faster than x is running. It's flying is faster than running. FOPC can be used to reason about a wide variety of problems, such as classifying objects. For example, we can use FOPC to define a predicate, which would be a bird, which would be x. That means that x is a bird. We can then use this predicate to classify objects as birds or non-birds. So if it's x, then it's a bird. If it's not x, then it's not a bird. Proving theorems. For example, we can use FOPC to prove the theorem that the sum of two numbers is always even. So again, in that instance, we would put essentially x would be even. So if it's x, it's even. If it's not x, then it's not even. Answering questions. For example, we can use FOPC to answer the question, what does it mean to say that it is faster to fly than to run? And then that's our equation that we're looking at up here, where we can use qualifiers, we can use everything, all, and then we can use greater than, less than, equal than. We can use all of the mathematical qualifiers, and then we use that little weird upside down A is for all and for everything, right? So we can use also all and E, backwards E for everything. And then we can essentially with those few additions, we're just taking regular math, regular calculus and regular math, and then we add the few additions to it, the upside down A and the backwards E, and then we that's basically it. Just it's that calculus plus that really. But so when we do this, essentially what we see is the outputs that we can get from the model when it actually thinks these things through is quite significant and quite amazing. So I've done a few posts and shown a few examples already of kind of what it looks like between for this model on a base level compared to with the FOPC. And then again, I'll link this in the description. So if you want to run this further and run your own tests on that, you're more than welcome to run and see, and you can see the actual differences. The things that I'll highlight for you are very specifically that FOPC does have it's so with this logical reasoning algorithm, you don't want to run it all of the time, right? And then so I think, like, I don't know, I think that there's something there. I could be, I don't know. It's just my, so I've had this hypothesis already without this testing that you shouldn't run this algorithm 100% of the time, right? And then so like I ran it. If I ask it questions like this particular question here, a customer is complaining about the price of our widgets. Can you use FOPC to think through the best response to the customer? And then so essentially like I run this prompt through, and it just flat out it doesn't want to answer this question. Like it just won't do it with FOPC. Whereas when I had FOPC before, the response that I gave before, and I removed the response now for this, but the response that it gave without any sort of FOPC prompting to like having it that type of query was a basic email. It wasn't a good email, and then so I was hoping that FOPC would improve it, but in that particular instance, it actually made the output worse. Because I logic that through. It's right like, and then so this particular request is very hard to put into FOPC terms. Like a customer is complaining about the price of our widgets. Can you use FOPC to think through the best response to the customer? Problem is that like, there's multiple variables within that, and they don't chain together well. So it doesn't like in utilizing this particular method of calculus doesn't work for this particular instance. And then so just highlighting, so my repositories that I've been building out in GitHub around this. So I have this repository, which is like decision theory. And then so within decision theory, I have essentially, I've been like kind of building this out and trying to map all of this out, right? Like this like logical framework and logical process for AI. And then my how this currently works within my framework and like what we're talking about here is that this is kind of like I utilize this and how I want the like a larger model to utilize this is as a backup algorithm. And then so very specifically how I came up with and like kind of like my reasoning and thoughts around this starting on this train of thought and these tracks were with the AlphaGo model, right? So like to me, I start and when I think about AI, kind of the very first instance that me personally, like had like some sort of exposure to AI that I can like solidly remember is when Deep Blue beats Kasparov in chess, right? Like that was like a big event for me as a kid. I was really into chess, and then like that made me like not into chess like as much for a long time afterwards, right? Because it's like it's a soft game, right? Like why would I want to play it? Like I actually went through that a lot, and then so then fast forward to 2016, and then you have AlphaGo, and then so when AlphaGo comes out, and then AlphaGo defeats in 2016 defeats the human champion in Go, and then so from 2016 until 2022, AlphaGo goes undefeated, right? Never loses to a human, and then it is looking exactly like chess in that instance, where it's like okay. AI has like AI like an AI model is never going to lose to a human again when it comes to Go. But then all of a sudden, there 2022, this like random guy like he's writing like a Vice article. He comes out and he uses essentially like a very like basic and amateur strategy that the reason why it throws off the AlphaGo model is because the AlphaGo model's never seen this strategy, never anticipated it. Like it was never included in its training processes, its training algorithms, anything to deal with this particular amateurish strategy because it was so amateurish that like even a child could logic through and process through how to defeat this strategy. But AlphaGo was literally never trained on it. And then so AlphaGo faces this strategy, freezes, and then loses to a human amateur. It will beat the best player in the world, like with no contest whatsoever, for years and years and years, and then all of a sudden just loses. And then so like that loss of AlphaGo brought up like a lot of questions around AI, like around thought, like how deeply does AI understand things, like things like that, right? And then so I dive deep into those things, and then so to me these algorithms are kind of like a response and like a solution to that problem within AI, like the like getting AI to actually grasp the information and think. So how this algorithm is designed to work, like this decision making algorithm, is that like the if you read through this long brick of text that I have that I've written about it, because I want to get all of it out, but essentially the very like first process of the algorithm is like if you're in that situation that AlphaGo is in, like you're in that situation where like you're in a game and then you see a strategy that you've never seen before, that's when this algorithm kicks in. Otherwise, this algorithm doesn't do anything, right? This algorithm is just there. But then so you find yourself in a situation and you're like, I have a problem. I do not know how to solve this problem, and I have never experienced this problem before. Okay, boom, now decision theory kicks in. So decision theory kicks in, and then that kickstarts the process of these algorithms. And then kind of like the overarching framework of decision theory is that these algorithms build on each other, and then so it's like essentially, okay, I'm in a situation, I don't know what to do, I've never seen this problem before. Okay, let's use first order precision calculus to first quantify what the actual problem is, and then let's quantify a problem, and then like as like what we're trying to solve for. And then once we do that, then we go through a decision tree process. And then now that we have defined what the problem is and we've defined what the solution is, can we actually solve this problem? If the answer comes out no, then let's go down further in the decision theory decision tree. If yes, then let's exit decision theory. But so if no, we're still in decision theory. And then what's the next step after that? Okay, we have a problem that we've never faced before. We don't know what the variables are and we can't solve it. So our next step is that we're going to use a Monte Carlo algorithm, and then we're going to simulate. We're going to first break up the problem into smaller problems. So we're going to take this big problem, and then we're going to do what we can using first we're going to, in that instance, we're going to use first order precision calculus to divide that problem into smaller problems. So if it's like a question of like what's the purpose of evolution would be like a big example, right? Like a big unsolvable problem. And then it's like, okay, I don't know what that is, and I'm not going to be able to solve for that. So what I can do is I can use first order precision calculus to break that problem up and chunk that problem into smaller problems about evolution. Like, does evolution have a purpose? I can make decisions around that, right? Like what is the evolutionary process? Like what animals look like? Is natural selection a subset of evolution? Like there's a lot of questions that I can spin off and I can split from that. So then once I have these like other underlying questions that I asked, and then the next step within that is that I kick in Monte Carlo algorithms, and then I in this instance I simulate essentially the answers to all of those questions, all of those subset questions, right? So I have this big unsolvable problem, I break it up into small chunks and these smaller little problems, and then I use a Monte Carlo algorithm to simulate the solutions, possible solutions for all of these problems. I pick the best possible solution that I've simulated from these smaller problems. I then conglomerate all of the simulated solutions that I've made for the smaller problems into a bigger problem, or into the bigger problem, and then I use that to filter, and then now I have some variables that I can plug into the equation for the bigger problem. And my answer is probably not going to be perfect, right? It's not going to be like the 100% accurate answer, but it's going to be better than 50-50 in that instance. Like it's going to be like it's going to move the bar and move the benchmark, like game theory. Like decision theory is like game theory, right? Like it's not going to be like it's not going to move the bar from 0 to 100, but it's going to move the bar. And then like that's what the whole point of decision theory is. And then it's kind of like computationally expensive for what it does. And then it's so you don't want to use it as like a general theory, but if there's a point where the AI model is like, I don't know what to do, I don't like all here, like here's your framework, it kicks in, here's the flow, you've got your full decision tree, you know exactly what to do, step 1, 2, 3, 4, and then run through the decision tree process. And then so that's essentially what we're looking at here. And then all like my every repository like really that I have built out around is all around logical reasoning, right? Like so, like every single one, possible worlds, algorithmic lines of flight, logical equivalency, logical tautologies, logical inference solutions, recursive first order logical inference, etc. Like it's all based off of this is all like these like these repositories are designed so that if you want to give a model like logical thought and logical reasoning capabilities, just use these like use the libraries here. That's basically it. So yeah, that's basically it. Showcasing essentially how first order, how essentially we can use first order predicate calculus to make models better, and then we've utilized the Phi 1.5 model to do this. And then so if you like this type of content, please like and subscribe. Thank you very much.